So this is problem 1 of the exam 1 prep for ES 110 statics. So this first problem, we're going to be solving a simple resultant force vector addition problem in 4 different ways. We're going to be solving it with triangle method, parallelogram method, law of sines and cosines, and the components. So 2 graphical methods and 2 computational methods. So again, here the problem states we have a 4 kilonewton force in the horizontal direction and a 10 kilonewton force 30 degrees off from the vertical. So the first method is the triangle method. And since this is a graphical method, one thing that we can do is come up with a scale. So what I'm going to do is since I don't have a ton of space here, I'm going to say that 4 kilonewtons is equal to half of an inch. So this force will be half of an inch, and then 10 kilonewtons, that would be 1 1/4 inches. So we want to draw our 4 kilonewton force. It's going to be half an inch, like so. And again, this triangle method, this is tip to tail. So we're going to draw the first force, then we're going to draw the second force at its head. And again, this is 1.25 inches, so something like that. So we're going to have 4 kilonewtons, 10 kilonewtons, and our resultant force is going to be from the tail of the first force to the tip of the second force. So just like that, and I'll draw that in red so it's very clear that that's the resultant. So now we have to do some measurements because this is a graphical method. So we're going to go ahead and measure this force. And I see that it's almost exactly 1.5 inches. So we're going to say 1.5 inches times the scale we used, which was 4 kilonewtons to 0.5 inches. This becomes 1.5. I wish I could do this in my head, but that's what calculators are for. This becomes 12 kilonewtons. So we know the magnitude of the resultant force is approximately 12 kilonewtons. And now for the angle, again, this is complete guesswork because this is a graphical method. And we could measure this with a protractor, but for this purpose, I'm just going to estimate it by hand. I would say that is about 45 degrees. So since it's 45 degrees from the vertical, it would also mean it's 45 degrees below the positive horizontal. So this is our answer. Now for the parallelogram method. The parallelogram method is pretty similar, except we don't need to put the vectors tip to tail as we did before. We can put them tail to tail. So we can leave them how they are on the initial diagram. So again, if we draw our force, our first force, it's going to be half an inch, 4 kilonewtons. And our second force is going to be 10 kilonewtons, and it's going to be 1.25 inches. And again, this is 30 degrees from the vertical. Now the whole idea of the parallelogram method is we draw parallel forces, or parallel lines to these forces. So we're going to move this over to the tip of that one and draw a parallel line of the exact same length, like so. That's approximately parallel. And then for the top force, I'm going to draw a parallel line of the exact same length, like so. And then we find the resultant by going from the origin to where those two lines meet, like that. And again, now it's time to measure because we're using a graphical method. So we'll go ahead and measure this line. And I see again, it's approximately 1.5 inches. And again, because we just did that calculation up here, we can say that our magnitude is going to be 12 kilonewtons. We estimate the angle by estimating this force. You know, I would say this is like 20 degrees. So it's going to be 50 degrees from the vertical, which means it's going to be 40 degrees below the positive horizontal. So 40 degrees below the plus x axis. So that is our answer using the parallelogram method. Now on to the computational methods. So first we'll start off with the law of sines, law of cosines. Now this method is a computational method, kind of as well as a graphical method, because we still do have to draw the forces in order to use this. So what we're going to do for this method is we're going to draw we're going to, again, draw the force vectors that we're trying to sum tip to tail. So we're going to draw, this doesn't necessarily have to be to scale, because this is computational. So we're going to draw our 4 kilonewton force, and then at the tip of that one, we're going to draw our 10 kilonewton force. And then we're going to draw the resultant tip to tail. And again, that comes from the triangle rule. But this, in this case, this isn't to scale. And this is our resultant R. So we know that the law of cosines says that, and we'll call this F1 and F2. And again, we know that this is 30 degrees from the vertical. So the law of cosines says that R squared is equal to F1 squared plus F2 squared minus 2 F1, F2 cosine of this angle, and we'll just call this angle theta. So to find that angle theta, we know that F2 is 30 degrees from the vertical, and we know that this is a right angle because this force is horizontal. So we can say theta is equal to 120 degrees because it's 90 plus 30 degrees. So we can fill in R squared is equal to, we know F1 is 4 kilonewtons, so 4 squared, plus F2 is 12 kilonewtons, 12 squared, minus 2, 4 times 12, cosine of 120. And we plug that into our calculator. And we get 208. But again, our resultant has to be the square root of that number. So we do the square root of the answer, vans, to get, oh, you know what? I'm sorry. I put in 12. This should be 10. Sorry about that. So let's recalculate that. That is 156. And the square root of 156 is 12.5 kilonewtons. Okay, well that's the magnitude, but what about the direction? What about this angle here we're trying to find? So we would be able to know that the angle from the horizontal that R is if we found this angle right here. And we'll call this angle, alpha. So the law of sines says that a side of a triangle divided by the sine of the angle that's opposing that side is equal to another side divided by the sine of that angle opposing that side. So it makes more sense if we write it out. So it's basically saying that, I'll write LOS here. Law of sines says that, for example, R over this angle, so R over the sine of theta is equal to F2 over the sine of alpha. And we know R, we know theta, we know F2, and we're trying to find alpha. So let's solve for the sine of alpha. If I'm just going to do this in one step here. So sine of alpha by multiplying sine, so by switching these, we get sine of alpha is equal to F2 sine of theta divided by R. So we can plug in some numbers here because we know F2 is 10 kilonewtons. We know sine. We know that this angle, theta, is 120 degrees. So sine of 120 degrees divided by R, which we just calculated to be 12.5. So we run those numbers. So 10 times the sine of 120 divided by 12.5 is 0.6928. If we take the inverse sine of that to get alpha, alpha equals the sine -1 of 0.6928. Make sure your calculator is set to degrees. And we get 43.9 degrees. So using this method, and again, remember that is this angle, an alpha, which is the angle between the resultant and the horizontal. So we can say that R is equal to 12.5 kilonewtons, and it is 43.9 degrees below the plus x axis. So that is our answer using the law of sines and the law of cosines. So let me grab another piece of paper here, and we will use components, which is the last method of solving this type of problem, and honestly, the one you're probably going to end up using the most in the future. So, again, we have our system. Let me just redraw it. 4 kilonewtons, 10 kilonewtons, 30 degrees. This is the y-axis, this is the x-axis. So first we're going to sum the components of the forces in the x direction. This is easy for this force because this force is completely in the x direction. So we'll call this F1, call this F2. So F1 of x, so F1 in the x direction is 4 kilonewtons. The force is completely in the x direction. Force 1 in the y direction is 0 kilonewtons because it has no component in the y direction. It is not vertical at all. For F2, we have components both in the x and y direction. So for F2 in the x direction, we have to use some trigonometry here. So we know this is 10 kilonewtons, we know this angle is 30. So our component in the x direction is going to look like that. So it's going to be F2x, and our component in the y direction is going to be like that, F2y. So we know this, we know F2, and we want to find this. So we do, this is the opposite side, so we're probably going to use sine, or we're going to use sine. So F2 of x is equal to F2 times the sine of 30. Because remember, sine is equal to the opposite over the hypotenuse. And in this case, the opposite is F2x, the hypotenuse is F2, so if we want to find the opposite, we multiply the sine of the angle here times the hypotenuse, which is F2, so that's why we have F2x is equal to F2 times sine of 30. And that evaluates to, remember F2 is 10, so 10 sine of 30 degrees. That evaluates to exactly 5 kilonewtons. And that is positive, so it's facing in the positive x direction. Meanwhile, F2 in the y direction, we're going to use cosine, because remember, cosine is equal to the adjacent over the hypotenuse. So in this case, the adjacent in relation to this angle is going to be this component. The hypotenuse is always F2, so that means if we want to find the adjacent, we have to multiply the cosine of this angle by the hypotenuse to get the adjacent. So we're going to do F2 times the cosine of 30 degrees, which is 10 cosine 30, which is 8.66 kilonewtons. So now we just have to do some final tabulation. We sum the forces in the x direction. We'll just use the Greek letter sigma to designate a sum. Sum of the forces in the x direction is equal to F1x plus F2x, which is equal to 4 kilonewtons plus 5 kilonewtons is equal to 9 kilonewtons. Luckily, I can do that math in my head. Sum of the forces in the y direction is equal to F1y plus F2y, which is equal to 0 kilonewtons plus 8.66 kilonewtons, which is equal to 8.66 kilonewtons. I'm glad I can do that math in my head as well. But these are just the components. We want to know the resultant and the angle. So again, so we know the resultant force is going to look like this based off of the components. We're going to have an X component of 9 kilonewtons and a Y component of 8.66 kilonewtons. Oh, and you know what? We should be doing arrows here. This is going to be down. This is going to be that way. This is going to be that way. Because we have 4 kilonewtons that way and 5 kilonewtons that way, we get 9 kilonewtons in the positive direction. Because we have 8.66 kilonewtons down, we have our resultant as 8.66 kilonewtons down. So that's why when we draw it, we can draw our final force, 8.66 kilonewtons down and 9 kilonewtons to the right. So to find the resultant of these two forces, our resultant will look something like this. And our resultant is just a matter of the Pythagorean theorem. So resultant is equal to the x component squared plus the y component squared, all square rooted, which is equal to the square root of 9 squared plus 8.66 squared, which is equal to 12.49 kilonewtons. And we want to find this angle. And we know from trigonometry that that angle is defined as the inverse tangent of the opposite over the adjacent. And the opposite in this case is the y component and the adjacent is the x component. So we're going to have tangent of negative, the inverse tangent of 8.66 divided by 9. Put that in your calculator, making sure that your calculator is in degrees mode. 8.66 divided by 9 is 43.9 degrees. So again, that is our final answer, and that matches quite well with what we got using the law of sines and cosines, as well as the graphical methods. We got a pretty good approximation. You know, this is a little off, this is a little off, this is a little off, but in general, because we drew everything to scale, a pretty good approximation.